Good afternoon, everyone. Thank you so much for attending B-Sides. Please welcome Rob King with his talk, There and Back Again, Discovering OT Devices Across Protocol Gateways.
Hello. Mic live? Yes, perfect. Hi, everybody. Thank you for coming out, and thank you to the B-Sides staff and volunteers. This is awesome. This is a cool venue, too, so thank you so much for coming. So, how did we get here? Said in the most talking heads way possible. Well, I'm sure when you read the title for the talk, you were like, just like me, not so long ago, you were probably like, OT and protocol and gateways and across. What does all this mean? And it's like, well, let's start with some definitions, because one of the great things about this part of our industry is that these terms are very fluid and overlapping and interesting. So operational technology is technology that affects things in the real world, right? The pumps and the valves and things like that. And includes things like programmable logic controllers, which are the ruggedized computers that work in high vibration environments with heat and molten metal surrounding them, not touching them usually, hopefully. And computer numerical control systems, which are even more ambiguously named because they're actually the machining things that spin and do cuts and stuff, but it just sounds like math. I guess it is math. And a lot of people will include things like medical technology in operational technology, but a lot of people don't. It's a very fluid kind of term. And industrial control systems are then specifically stuff for doing industrial control. And then SCADA, or supervisory control and data acquisition, which I actually have a colleague, she has a shirt that says SCADA, but it's written in like the Sega logo. So every time I say the word SCADA, I'm always like SCADA, but I never quite do it. I want to though. SCADA is the computers that do the actual control, and one of the sort of the hallmarks of SCADA is having a simulacrum, sort of a diagram of how things work and a model of how things work. Now, what's interesting is I've had plenty of people way smarter than me, that's most people, way smarter than me, who have used these terms differently, and other smart people who have used these terms differently as well. So I know that some of you out there are maybe looking at these definitions and you're saying, well, actually, and I've heard all the well actuallys. So just we're going to stick with OT for this talk, and if you disagree with me, then that's okay. Come tell me, and we can nerd fight about it. It'll be great. So when people think of OT nowadays, right, operational technology, factories, they think of this sort of cool mission control thing that looks like it could be coming out of the Apollo missions. And this is part of it, and it looks super duper cool. This is from a manufacturing plant in Germany, I think, and I don't know what they're making, but I love the photo. They even look like they're wearing like Star Trek uniforms. It looks super cool and high tech. And this is definitely part of it. This is the technology part of OT. But what people kind of forget is that at the other end, there's the actual operational devices, the old school things with gears and valves and pumps, and they make noise and they spin and they vibrate and it's crazy. And there's a lot of history there that maybe we kind of need to talk a little bit about how we got from where we started to here. And so operational technology, I mean, if you want to get down to it, it's like the first time somebody hit a rock with another rock, right? But we've come a long way since then. But it used to be that operational technology it started out with maybe the conveyor belts that you would get on assembly lines to keep things in sync. Or you might have a single large steam engine or water wheel, and then ropes and pulleys to convey the force and the energy around to keep things moving. Have you ever been to one of those restaurants where all the fans are on like the same belt? It's kind of like that. It was pretty cool. Not that I saw it personally, obviously. Not that old. But then it kept moving on until you got to wanting to have computerized control, more intelligence behind this, not just gears and clockwork, not just off and on. And so we started getting these sorts of things, these little panels that could control a specific part of the control loop, a specific part of the factory floor, or one machine or whatever. And this was, of course, a big advance. But if you wanted to control it, you had to physically be there. You had to walk over and push a button, or take out a fuse or a relay and move it around and do all sorts of crazy things, but you could still do things like, I want to make this go faster, push, push, push. I want to make this go slower, push, push, push. Much easier, much better, much finer grained control. But then we wanted to, what if we got even more control? What if we made it even better? Well, then we introduced the concept of programmable logic controllers, and so PLCs. And PLCs are these ruggedized computers, like I was talking about, that are designed to bring, the full panoply of Turing completeness to the concept of industrial control. And it's super great, and they work well, and they're universally everywhere. They're called programmable logic controllers, not computers. I don't know why. For those of you out there, I'm going to digress for a second because I'm super history nerd. It's like when DEC called the digital equipment called the PDP, and not a computer, because computers were expensive and big, and the PDPs were, by today's standards, expensive and big, but they were much smaller and cheaper than IBM's computers. So programmable logic controllers then let you start controlling things at a distance and monitoring things at a distance and doing more complicated things. And right about 1978-ish, Modicon introduced the Modicon field bus. So it used to be that you'd have these devices. If you wanted to monitor them or control them remotely, you would have to basically run a set of wires to each one, right? And Modicon wasn't the first to come up with the idea of a bus or even the first one to do it in the industrial control setting, but they were kind of the first really big standard player. So a bus, it's just a shared medium across which you can send messages and multiplex this medium between potentially many senders and potentially many receivers, right? So now you can get away with just having one set of wires. And so Modicon, the Modicon field bus, would let you even just daisy chain serial connections from one device to another. But when you did that, you would need to have some way of disambiguating which device you were talking to, because now you're not talking across one set of wires to one specific device, you're talking to potentially many devices. So with buses comes the concept of addressing and collision detection and, reserving the bus and making sure no two things talk at the same time, because then it's chaos, right? And with that comes the concept of protocol adaptation. So now you've got this Modbus device, Modicon field bus, Modbus. You've got this Modbus device that's talking to a controller, which is being controlled by a human or monitored by a human or whatever. But then this device is potentially talking to some other device that doesn't speak Modbus, right? It's talking to a pump or a valve, or it's maybe talking to another intelligent device, but it just doesn't speak Modbus. So now you have to adapt the protocol from Modbus to something else. And then these protocols, every vendor had one, and they were all different, and they ran over different media, and they used different, communications protocols, and they used different connectors, and of course, it was just chaos, right? So what we're seeing now is this big push towards convergence. And so convergence in this case is, it used to mean, again, if you're super old, it used to mean having a cable box that was also a web browser. You may remember that, set-top convergence. Yeah, I'm dating myself there. But we're now talking about the convergence of IT and OT. So information technology and operational technology. And it used to be that OT was considered to be the IT in the non-carpeted parts of the building, right? It used to be that it was IT wearing a hard hat, but now that's really true. It's now falling under the purview of CISOs. It's falling under the purview of CIOs of the IP world, because things are converging on IP protocols. So IP, remember, IP wasn't always the standard. Like Modbus came out in 1978, and TCP was not standardized until 1982. And even after it was standardized, it wasn't necessarily going to, nobody was sure it was going to take over the world, right? It was the internet protocol designed to communicate between multiple networks. Those multiple networks might be speaking IPX or DECnet or the bag of eldritch horrors that was IBM SNA, which token ring was nice, but but now IP has taken over the world. IP and Ethernet, for the most part, taken over the world, and it's become a commodity. And so that's great, because now all of these industrial protocols are starting to migrate on top of these commodity technologies. And that's great, and that has benefits and detriments, but one of the main benefits is that these devices become more accessible. You can reach them more easily. They can be integrated with existing networks more easily. You can communicate with them remotely. That's all great. The biggest downside is you can, in fact, communicate with them remotely. So we've done some studies, and a lot of people have, and it turns out that there are thousands of OT devices on the public internet. You should not have your OT devices reachable on the public internet. This is a really, really bad idea. A lot of these devices, security was an afterthought. Security wasn't even an afterthought for a lot of these devices. They were designed to work in a factory with a grade separation. The only way to control them was from the factory floor or from the control room at the factory. There was no concept of, please authenticate me. Let's have cryptographic device identity attestation, right? These systems were not designed to even have that kind of CPU power. They couldn't do it. So it's getting there. We are getting better, which is great. But for a lot of these devices, there's no concept of login. There's no concept of password. Or if there is, it's very rarely enabled. And even if it is enabled, they're trivial to bypass. So we've seen quite a few. For example, there was automatic tank gauges, which is a protocol used, not surprisingly, to read tank gauges, like big industrial tanks of fluids, right? Super common at like gas stations. So this is one of the protocols that's used to determine how much gas is in like the big tanks underground. And it was also super frustrating because this heat map shows just how many automatic tank gauges are accessible on the public internet, and it's huge. And it was super frustrating because I was doing this research and I found all this great stuff. And I work with one of my colleagues who is absolutely brilliant, and it's always frustrating because I'll do something and I'll be doing this research and I'll come across this perfect piece of code or this little article or something, and I'm like, oh, this is awesome. This is exactly what I wanted. And oh, it looks like they already kind of started it 10 years ago. And then I find out that it's exactly what it was, and it's the guy I work with, and you know who you are, HD, but he did something like this quite a while ago. But super interesting, and yes, you can go and find out all sorts of gas station information publicly, but it's not just gas stations. We found, and of course I'm not going to show you the IP addresses because I'm not a monster, but we found all sorts of things publicly exposed on the internet. PLCs, power devices, we could shut things down remotely. Not that we would because we're nice people, but these things are exposed on the public internet. Not a good idea. But this is all due to this convergence of OT and IT. So how do we discover these devices, right? So once you're on an IP network, you're now having to communicate through you're communicating with this IP network, but you're now having to do this protocol adaptation because you're still speaking these older industrial protocols that have just been sort of brought up to the IP world, which is great, and I love it, and it's awesome. But so the easiest way is to work with Modbus. This is kind of the first easiest example to give. So Modbus was originally designed to run over serial connections. RS-232, RS-488, a lot of the other RS standards. And so they would even be daisy chained along. And you would pass a message, you say, hey, I want to talk to device 14. And so you send the message down the serial line, and the first device would say, oh, I'm not device 14, I'm going to forward it on. Eventually we get to device 14, and device 14 would come back. And there wasn't any need for identifying these things because you already knew what they were. You had to go physically set jumpers and stuff to set their addresses. So you should know what they are. So the earliest versions of Modbus did support only on serial lines, only in the serial version of the protocol. They did support tell me your address, so that if you had a direct connection on a serial line, you could say, hey, Modbus device at the other end, I'm just going to send it to address 0, which is, nothing. Please tell me what your address is, and it would tell you back. That doesn't work for Modbus TCP. Modbus TCP is a much nicer protocol, though, in that they added the concept of the Modbus encapsulated interface, which is always fun to say. And so exactly what it sounds like, it lets you encapsulate a more complicated message inside a single Modbus frame, single Modbus command. Because the original Modbus protocol, super simple, right? It's designed to be parsed by a system from 1978. So it lets you, as part of the payload, just give another command with a richer set of messages or objects or whatever. And then if a device doesn't understand it, it'll just ignore it because it's an unknown command in the command field, and the payload goes away. But this Modbus encapsulated interface supports the report device identity command. So if you want to discover what a Modbus device is, you can say, hey, Modbus device address 15 or whatever, please tell me, here's a Modbus encapsulated message, give me back your report device identity. And it'll say, okay, sure, here you go. And that reports it back as a set of objects, which is pretty simple. You can say object 1 is, product code, object 2 is product name, but it's stateless. So it'll say, yes, here's the first object, object 0, next object is object 1. And so you request object 1. It says, okay, there's object 1, next object 2, or there are no more objects. We did have one that was really fun in that there was a bug where it would say, okay, next object is like 4, and then so you get next object 4, and then say, okay, I'm object 4, next object is 3, and so you go back, and it's just like the DNS compression pointer bug, which if you've never dealt with that, that's a lot of fun too. But the point is, Modbus TCP, there is a modern way to discover these devices, and you can discover things across the protocol gateway by simply specifying an address that you can determine is on the other side. And the address space is not huge, so you can even poll it if you want to, although, maybe not. But so let's move on to something that's a little bit more complicated. This is the Distributed Network Protocol 3, which apparently there was a 1 and 2. I've never used them. DNP3 is the sort of de facto protocol standard for electrical distribution networks in North America. And when they ported it to TCP, to run on top of TCP, they literally just took the entire stack of DNP3 and set it on top of TCP. So DNP3 has its own transport layer and its own addressing layer and its own connection layer and its own application layer. And it's all just kind of shoved in there, and it's even still blocked and checksummed inside the TCP stream. Super fun to work with, really, really complicated. And this is a diagram just so you can kind of get an idea of how complicated this protocol is. But I do love writing protocol parsers, and it was a lot of fun to write this one. But the problem with DNP3 discovery is that and DNP3 does support, from the get-go, it does support a collection of, please tell me who your manufacturer is. There's these numbered attributes, and you say, hey, please tell me the value of numbered attribute 57, which is your hardware version, you'll get it back. That's all well and good. The problem is that you have to know the DNP3 address, not just the IP address. So if you know the IP address of the DNP3 gateway, that's only half the battle. That's not even half the battle, in fact, if you do the math. So DNP3, like I said, literally just put the entire DNP3 stack on top of TCP. So they didn't even bother to add a little bit of other stuff. So you have to, when you connect via IP, you still have to know the DNP3 address, and there is no way to discover it except by the couple of ways I'm about to tell you. So a DNP3 address is 16 bits, but some of them are reserved, and you still roughly have 65,000 addresses to work with. Secondary devices and primary devices. A secondary device will only talk to its pre-configured primary device. It will not respond if a message comes at the DNP3 layer from another device, even if it's coming from the correct IP address. So it's a grade separation inside the protocol itself. And this is usually configured at boot time or whatever. There's no DHCP for DNP3, although what an acronym that would be. So you have to guess both, if you want to communicate with it and get information about it, you have to guess both the primary and the secondary addresses. And with 65,000 possible addresses, that comes out to 4.2 billion possible combinations, which you should not do. That's a bad idea. So the good news is that usually, at least in all the DNP3 networks I've seen, the addressing, they keep it towards the front of the range. So usually the addresses start at 1, and usually the addresses don't exceed 512, right? Obviously, different networks could do it different ways, who knows, right? But even with just 512 addresses, you're still going to end up with 262,144 addresses, which is more than address pairs, which is more than you're going to want to deal with. So what we have discovered is that you can kind of lean on it's not a safety feature, but it's an interesting sort of hello that you get from about 70% of DNP3 stuff that we've tested. So DNP3 has this concept of an unsolicited response, which means it's responding to a question that wasn't asked, which I do all the time. So with DNP3, when you connect, it will immediately send out a response. If you connect on IP, it will immediately send out a response saying, oh, I'm in this error condition or no error condition. My clock is synchronized with the primary or it isn't. But the benefit there is that when it sends out that message, it's going to send it from its DNP3 address. The DNP3 packet is completely just sent on the wire. So you'll see the DNP3 framing with the DNP3 address. The source is the device you're talking to, and the destination is going to be its designated primary device. So you can simply reverse that and you can say, aha, I now know what I'm supposed to do. I can now spoof this primary. And it also lets you narrow down the range of addresses you have to look through because, if you're getting a response from device 7, and there's probably devices 6x43, and there may be a device 8, right? So super, super useful there. But the big one, and my favorite, is Ethernet IP and SIP. And this is the worst. So we were talking about like bad terminology earlier or conflated and ambiguous terminology earlier. This, to me, personally takes the cake. So Ethernet IP is barely Ethernet and is not IP. And SIP is, there's the critical infrastructure protection, which is a common set of regulations in OT. And then there's also SIP, the common industrial protocol. And I'm talking about that one, not the other one, but I have to ask every time. When somebody's like, do you support SIP or are you SIP certified? I'm like, I don't know. Which one? So SIP is an abstract protocol built around objects and interfaces. And it's the height of like late 90s, early 2000s when everything had to be object-oriented, and it's quite pretty. But it's this abstract protocol that is then concretized, adapted to different transport and physical layers. And Ethernet IP is the adaptation of SIP to Internet Protocol and Ethernet. So you literally have Ethernet, Internet Protocol, Ethernet IP, and it's you got IP, Ethernet. It's really, really confusing when you're talking about it. So usually it's abbreviated as ENIP, which helps a little bit. But there's other applications, adaptations of SIP. You have DeviceNet, CompoNet, ControlNet, all these different ones. But what's cool about it is that makes it a little bit abstract, which we'll see. But at the lowest level, so the Ethernet IP level, you don't even have to talk SIP to discover something that's directly connected via Ethernet IP. It's still going to speak SIP. It's a SIP device, right? But you can, it supports discovery at the Ethernet IP level, the actual IP addressing level. So you can send what's called an Ethernet IP list identity command. And you can see, a Wireshark dump here, and you say, okay, here's an Ethernet IP list identity command. Please tell me who you are. And the device will come back and say, oh, yes, of course, I am a Rockwell Automation Allen Bradley programmable logic controller, and my version is this. It's super great. You can even, which is really, really nice, send this as a broadcast UDP packet and just ask everybody on the network, please, come to me, my children, and tell me what you are, and you'll find it all out, and that's great. But Ethernet IP, that's only getting you what the protocol gateway is, which is great, don't get me wrong, but that's where a lot of this stuff stops. And I take it as a personal affront if there's a device on a network and I can't find it, right? Like I really, really want to see everything that's out there. So the way, and there's Ethernet IP can work with lots of different devices. This is one we have in our lab. It's an IO-Link device, and it speaks Ethernet IP, and you can just say, hey, Ethernet IP, tell me who you are, and you get it right back, which is great. And this is another example of a protocol gateway that is talking to something completely different, right? This is actually talking to IO-Link, which is another industrial protocol that isn't actually an application of SIP, but this adapts IO-Link to Ethernet IP and SIP, and it's all super great. But what you'll often get is these devices that have multiple, you'll have the Ethernet IP adapter, right, the protocol gateway, but then you'll have another bus or even another whole other network speaking maybe even Ethernet IP behind that device, but it's a whole private network that you can't necessarily see. And when you're talking to the Ethernet IP protocol adapter, you'll say, hey, tell me who you are. And it'll say, oh, I am this, but then it's not going to necessarily tell you about the, 8 devices in a trench coat that it's got behind it. And I want to know about those guys, right? So what you can do, Ethernet IP supports this concept of a connection manager object. And the connection manager object, not to keep you in suspense, it manages connections. But you can say, okay, I would like to, talk to this Ethernet IP device, this gateway, say, okay, please give me your connection manager object. It says, okay. You say, all right, please tell me about your connections. It says, oh, sure. It says, okay, please build a connection for me from, my management station to this device. And then I want to connect to, and then you send a message that says, okay, now I want to connect to the identity object on that device. And what'll happen is the connection manager, it's almost like a VPN, right, in this industrial network. And you say, oh, okay, sure, I'll forward your connection to the identity object through myself, and then forward the response back. And the identity object is, requesting all the attributes of an identity object in SIP is almost equivalent to doing a list identity in Ethernet IP. So you'll get pretty much the same information back. But what's neat about it is that this could potentially be going across like 4 different media, right? Like this could be talking over a backplane and then talking over a device net, or even a whole other, there might be an industrial firewall in between, and then you're doing NAT. It's super, super cool. And in fact, that's kind of what you can see in this example here is when you're talking on the backplane, when you're talking to the connection manager object, you can say, hey, please, give me this connection to the backplane. And so you'll talk about the backplane, and then you'll say, oh, I'm going to keep building the connection and say, now I want to go across device net to this device. If anyone out there who's old enough to have had an exclamation point in their email address will know that you have to build the path yourself, right? You have to say, okay, now I want to go to the next device, tell me about yourself, go to the next device, tell me about yourself, go to the next device, tell me about yourself. And it's like you're a puppeteer because you're talking over a serial connection over here, and you're talking over a device net connection over here, and you're spreading your fingers. It sounds nefarious. You're spreading your device discovery throughout this hidden network. And but what you have to do is you have to build that path in this route path specification in SIP. And so the route path specification is extremely rich. It's super, super complicated. But the route path, each segment is identified as, okay, you can say, I want to talk to the backplane slot 4, and then maybe the device in slot 4 is another Ethernet IP adapter, and it's got its own IP address, and it's talking to an IP address over there. And so you have to say, okay, I want to go, first step is backplane slot 11. Next step is Ethernet IP adapter. I want to talk to IP address 192.168.7.4. And you just keep building out your path until you discovered every single thing in that hidden network. And so this is an example of when I was walking the backplane, which sounds like life in the fast lane if you say it fast enough. So it's stuck in my head now. But you can see that this was talking to the protocol adapter, the general purpose discrete I/O, and then it's speaking to the 1734 PLC, and you see there's an RS-232 device in there. So this is actually, I'm having to transit from Ethernet all the way to RS-232 classic serial to talk to another device and get information about it. And I love that. That just makes me so happy, which it does. It makes me happy. I think it's super, super cool. So the idea is that you can, in fact, discover devices on these networks, even through these legacy protocol gateways, right? These protocol gateways are not where you should stop. If you're trying to really find everything on your network, don't stop at the protocol gateway. Keep going. Now, the fun part is these standards are not really super available. Like some of them, like the Modbus standard, just go to modbus.org, download it. It's a short, small PDF, read it. It's printed out. It's on my desk. It's only like 6 pages. Do it. DNP3 also publicly available, though there is no hard and fast specification as to what attributes correspond to what, like vendor name and stuff, but everybody kind of standardized on the Schneider Electric numbering, so yay. But the SIP stuff is, you have to, about half of it is publicly available, which is great, and about half of it you have to be a member of ODVNA, which, as far as I can tell, stands for nothing. I think the A is association, but I literally think the rest of it is used to mean something and now means nothing. And if you're not a member of that, there's a lot of cross-referencing that you have to do to things that you might not have, and so you have to do a lot of reverse engineering. But the point is you can do it. I can do it. I did it, and you're all smarter than me. So go forth and discover things on your OT network, BAS protocol gateways. Thank you. Hey, I made it through time. Okay. We have 2 minutes.
Thank you so much, Rob.
Questions, yeah. Any questions? We got 2 minutes.
We have one question if you want to go off the Slido. We have a few.
Oh, perfect.
Okay.
Oh, okay. Yeah.
they're anonymous, so I'm not sure if it's yours. How does the pump know that the signal to turn on, which it is receiving, is authentic and appropriate?
The answer is it probably doesn't. There is, especially in SIP, there is the concept of authenticated SIP and SIP-S and things like that. But once it gets down to that level, that often is not even enabled in a lot of networks. And once it gets down to that level, it's just kind of implicitly trusted that it should do what it should do. This is why you should not have your OT stuff exposed to the public internet. Please, please don't do that. So.
All right, one more. How does the system know that the signal from a sensor is authentic and accurate?
Again, it probably doesn't. And in fact, going the other way, it's even less. A lot of times those devices authentication usually is, if it's enabled at all, usually goes from the top down. Coming from the bottom up, there's considerably less. But you can do it. There are, especially in SIP, there are ways you can, but it's often not enabled.
I think we can squeeze this last one into about how many of these internet exposed OT devices are actually just honeypots.
We did check, and so what's funny, for like the ATG ones, you can tell if they're honeypots or not because the honeypots will respond faster. Because these devices are so old and slow that if you connect to them and they respond immediately, you're like, oh, that's a honeypot. So there's probably around, at least in my data set, we had around 10,000 that I would consider legit. So, yeah.
Thank you so much, Rob.
Thank you, everybody.
Thanks for attending, folks.